are posting the recording. We're posting the recording on Klaus' YouTube channel. That's what he proposed. So it will be public. Um, so this is work with Pietro. I also see in the audience Fabio Franceschini, who gave us a lot of help at the beginning when we were thinking about how to approach the estimation. So I would like to thank him in public. So what is this paper about? So um, the conventional wisdom in growth theory is that if we want to generate a constant steady state endogenous growth rate, we need constant returns to the growth driving factor. If we have diminishing returns, then growth disappears. If we have increasing returns, then growth is ever increasing, and ultimately the model explodes. With this paper, we overturned this understanding of growth theory, and we showed that we can generate a constant steady state endogenous growth rate even if we have diminishing or increasing returns to the growth driving factor. What allows us to do that is a fairly standard assumption that is a free entry condition that introduces endogenous competition. And because there are endogenous competitive pressures, what will happen in the model is that the returns, the firm level returns to investment will remain constant in steady state, even in the presence of non-constant returns to the growth driving factor. An implication of the model is that the speed of convergence to steady state will be asymmetric, and that has some theoretical implications that I will illustrate. And also, that is what allows us to go to the data and estimate what is the degree of returns to the growth driving factor. So let me just start by defining what we mean by endogenous growth. And in this audience, there shouldn't be any need, but let's do it regardless. So what we're going to be looking for is a constant growth rate of income per capita in steady state that is generated within the model. So that is endogenous, and that is subject to policy action. So that reacts to the various parameters of the model. Some early criticism of endogenous growth theory is that it requires, as I said, a linearity assumption, a knife edge condition. So in other words, it's not robust. And a proposed solution in the literature has been, well, let's introduce diminishing returns. So we have a thicker set of parameters to deal with. But what that does is that it kills endogenous growth. So in this paper, what do we do? Well, we think of innovation as the driver of growth in two dimensions. One vertical that is improving product quality, firm level product quality, and that's going to be the driver, the engine of growth. And one that is horizontal, that is creating a new product that didn't exist before. Now, you that are all familiar with endogenous growth theory, and you know that this is a fairly standard way to proceed. And this distinction into the two different dimensions of knowledge is important because it sterilizes the scale effect. So because there is a dilution of market share due to horizontal innovation, that counters the expansion in market size driven by population growth. And as a result, it preserves constant returns to investment at the firm level that gives us a constant growth rate of income per capita in steady state, even in the presence of population growth. The insight of this paper is essentially the same. What horizontal innovation will do is that it will sterilize the scale effect, but in addition, it will also counter the non-constant returns to the growth driving factor. One implication, as I said, is that we find asymmetric speed of convergence. Because the returns are non-constant, then convergence dynamics will differ depending on whether we are converging to steady state from above or from below. Finally, because the speed of convergence is non-constant, we can actually go to the data and estimate whether there is acceleration or deceleration in the speed of convergence. it will end up being the case that the coefficient, the parameter associated, the parameter that gives us the returns to the growth driving factor, vertical knowledge, is uniquely pinning down the coefficient that associated with the nonlinear term in the convergence dynamics. And because of that, we will be able to identify that parameter from a fairly simple regression. Now, let me spend a little bit of time on the literature because I found it interesting when I was doing that. And so there's a fairly long gap in between Solo 56, the classical growth model, and the Romer 1990 model. And an interesting question to ask is, what can explain this gap? After all the ingredients of endogenous growth theory were available well before the 1990. Arrow 1962 talks about endogenous knowledge. And I was actually quite surprised when I read Nordhaus 69, because it talks about knowledge in the same way as Romer. The big difference, there are two main differences between Nordhaus 69 and Romer 1990. One is Nordhaus doesn't have monopolistic competition because the mathematical framework is developed a bit later. But most importantly, there are not constant returns to knowledge. There are only decreasing returns to knowledge. And had he just assumed constant returns to knowledge, we would have had endogenous growth theory in 1969. Then monopolistic competition gets developed. So Grossman and Helpman and Jude start working with this model with monopolistic competition. And so the question remains as to, why do we need to wait until 1990? And I found this answer from Stiglitz and from Romer himself, reflecting back about the origins of endogenous growth theory. And what they both say is that the profession was obsessed with robustness. They really didn't want to deliver a result that relied on setting a parameter equal to a specific value, and any slight deviation from that value would kill the result. And as a result, that's what explains why we didn't have endogenous growth theory for a long time. Now, Romer 86 is instrumental to lead us to Romer 1990, because it shows that, well, we can in fact have a model with increasing returns. It just, for convenience, we will work with constant returns. What increasing returns would do is that it would create a trend, an upward trend in the growth rate over time, but at least we can have an endogenous growth rate of income per capita. Still, it remains the case that until Pietro's paper in 2018, to generate a constant and endogenous steady state growth rate, you needed constant returns to the growth driving factor. Pietro 2018 has the same mechanism that we will show today, and it shows that you can also have increasing returns to the growth driving factor. What we do in this paper is we show that we can have endogenous growth even with decreasing returns to the growth driving factor. Plus, we go some steps above in talking about the speed of convergence and in estimating the relevant parameters. Before I dive into the model, let me give you the basic intuition for our mechanism. The model will deliver the following reduced form aggregate production function. So income per capita will be a function of Z, vertical knowledge, N, horizontal knowledge, L, labor, and omega, that is a fixed factor that you can include any fixed factor. You can think about it as land. Importantly, we do not need to impose the only imposition we make on kappa is that it needs to be positive. We don't need to impose it being equal to 1. We don't need to impose it being bigger than 1. We don't need to impose it being smaller than 1. All we need is that it's positive. Now, what's the basic intuition. We're gonna get a constant steady state endogenous growth rate if we have constant returns to investment at the firm level. And the returns to investment at the firm level will depend on the composite variable X. So let's analyze what the composite variable X tells us. Composite variable X is Z to the power kappa minus 1. So in the canonical case of constant returns, that term drops out because kappa is equal to 1, minus 1, it drops out. And what else do we have there? Well, we have the fixed factor of production that doesn't change, so good. And then we have L at the numerator and at the denominator. Canonical case of kappa equal to 1, if L and N grow at the same rate, then X is constant and we have endogenous growth. That's the standard insight in the literature about horizontal innovation sterilizing the scale effect. Now, what happens if kappa is different from 1? And it can be below 1, it can be above 1. Well, as long as we have N growing at a different rate than L, and in particular at a specific different rate from L, at a rate that is high enough to compensate for increasing returns or low enough to compensate for decreasing returns, then we can still have constant steady state endogenous growth rate. In other words, the market share effect will be the one that sterilizes both the scale effect and the nonlinear returns. Let's go into the model. Now, just a brief description. Household, very standard problem. So I'll show you in a second. There's a final sector that's perfectly competitive and uses a CES aggregator to assemble the intermediate goods into the final goods. Again, fairly standard. And the intermediate sector where all the action is, there's going to be monopolistic competition, standard in endogenous growth theory, and then the two types of innovation. Vertical, in-house R&D to improve product quality, and horizontal, that is endogenous entry subject to a free entry condition. The household problem, as I said, is standard. We use a log-log specification, maximize utility subject to a budget constraint, and from here we derive the usual Euler equation and the labor supply curve. One thing I forgot to mention, we allow for positive population growth. The final sector, again, fairly standard. There is a CES production function. The final sector assembles intermediate goods that are scaled by their quality. Kappa, as I showed earlier, are the aggregate returns to vertical innovation. Alpha instead are the private returns to product quality. Kappa minus alpha instead is an externality. Importantly, I repeat, we do not need to impose kappa being equal to 1 or only bigger than 1. All we impose is that it is bigger than 0, that it is positive.
Filippo, Filippo, so may I ask a question? Hi.
Yeah.
So going back to the previous slide, do you really need endogenous labor supply or?
No, we don't need endogenous labor supply. We just
have
want
it in
to show
equation
that even if we have it, there's no problem.
It is not really playing a role here. It's just
no, that's not
what
does the job.
Okay. Yeah, sure.
Maybe it's useful, no, for your calibration.
Yeah, so we don't calibrate the model in this paper, but for sure it is useful for the calibration.
Okay.
So here we derive from the profit maximization in the final sector, we derive a labor demand, and we derive a demand for each intermediate good. Monopolistic competition in the intermediate sector. And so, as I said, this is where all the action is. What does the intermediate sector do? They produce, and they produce 1 unit of a good with X units of the final good. Why do we use X units of the final good? Because it makes everything very simple. And they face a fixed operating cost. The intermediate sector also performs R&D. They use units of the final good to produce new vertical knowledge that translates into product quality. And they maximize their firm value, subject to those constraints. You can see in equation 12 the operating profit that is a function of z. And again, I want to stress returns are to z are decreasing, constant, or increasing. We don't have to impose that. We do the profit maximization for the firm. Now we introduce, as you see from equation 13, competitive fringe. This is an assumption that is not really needed, but it is very useful for calibration. That's why we have it here. Although we don't do calibration of this model, we just hope that people will use it and for quantitative analysis, and therefore we want to keep it as close as possible to the quantitative version that people would use. That's why we have this particular assumption. But most importantly, we derive the rate of return to vertical innovation that's given by equation 14. And we want to concentrate on that equation. In fact, for most of my talk, I will focus on that equation. What does that equation tell us? The rate of return to vertical innovation is a function of parameters and of quality adjusted firm size, X over Z. It is increasing and it is linear in quality adjusted firm size. Importantly, what will end up being important is that to deliver endogenous growth, we need to deliver a constant rate of endogenous growth in a steady state. We need a constant rate of return to vertical innovation. And so it will have to be the case that X over Z is constant in steady state for us to have a constant steady state growth rate. The equilibrium is symmetric under some conditions that have been studied before. So I'll move on from there and I'll move to the entry problem. Entry is very standard. Entrants pay a sunk cost to enter the market, to develop a new variety of a product. The entry cost is beta times X, Y times X, because the cost of production is times X. Therefore, the cost of entry will be times X, such that we preserve the trade-off between production and entry constant, even in the presence of growth. The asset pricing equation 15 regulates the returns to entry. What does it say? It says that the rate of return to entry is equal to dividend plus capital gain, very standard equation. And we have a free entry condition, of course, that is binding when entry is positive, and that's given by equation 16. By combining all that we derived so far, we end up with the rate of return to entry that is a function of what? Well, a function again of X over Z, and that's the important part, the growth rate of X, and lowercase z, which is the growth rate of average quality. So how do we get, what would we need to verify in order to ensure that there are constant returns to horizontal innovation? We would need to verify that there is a steady state for X over Z, that X grows at a constant rate, and that vertical innovation grows is constant in steady state. Okay, so this is ultimately where we're going. We impose general equilibrium conditions. These are very standard, therefore I will not devote time to this. And next we aggregate everything up. We aggregate everything up so that we end up with a reduced form aggregate production function, equation 17, that is, in fact, the one that I showed you right at the beginning of my presentation. So aggregate output is a function of n, number of varieties, z, average level of vertical knowledge quality in this economy, L, labor, and lambda, the fixed cost of production. Equation 18 is important because it tells us that, well, we can prove that C over Y jumps, the consumption over output jumps to its steady state. And that's important because it tells us that the labor supply is going to be L star at all times, that is dependent exclusively on parameters, therefore it is constant. Therefore, what do? We log differentiate equation 17, the reduced form aggregate production function, and get equation 20. Equation 20, what does it tell us? It tells us that aggregate output grows at a rate that depends on lambda, exogenous rate of population growth, and the horizontal innovation rate, and z, the vertical innovation rate. How do we have constant output growth? If, well, lambda is constant by assumption, if n and z are constant in steady state. So let's try to get there. Now, as I showed you before, ultimately, what is very important to have constant returns to investment is the variable x over z. X over z is what? Bunch of parameters that we compress into var pi multiplied by a bunch of variables. That bunch of variables, we call it lowercase x. So what is lowercase x? It is what I showed you right at the beginning of the presentation. It is vertical knowledge to the power kappa minus 1. It is uppercase lambda, that is population level. And it is divided by n, that is the number of varieties, the number of products in this economy.
I have a quick question.
Yes.
I have a quick. Does this lowercase x, do you have what I could call an economic intuition for what it is? That would be helpful if there is.
Yes. So it's part of quality adjusted production. Part of quality adjusted production. When kappa is equal to 1, it is also population size.
Can I chime in, knowing John? John, knowing you, the answer you're looking for is that the marginal profit of the firm is proportional to X.
Yeah, that's just what I was looking for. It'd be good to put that in if you don't have it.
Yes.
Yeah, I think I think we can put it in
because of the Cobb-Douglas structure.
Mm-hmm. Okay.
So when you look at X, you're looking at the variable that determines the marginal profit, the increase in profit due to a marginal increase in knowledge.
Okay.
All right. So now that we have lowercase x, what can we do? Well, we can rewrite the returns to vertical innovation, equation 22, and returns to horizontal innovation, equation 23. What do we see is that, well, if there is a steady state for x, then returns to vertical innovation are constant. That's what we're looking for. If returns to vertical innovation are constant, then it will be the case that the rate of vertical innovation, so lowercase z, is going to be constant as well. What does it mean? It means that we would have a constant rate of return to horizontal innovation as well, given from equation 23. So that's ultimately where we're going. We want to demonstrate that we can have, regardless of whether kappa is smaller than 1, equal to 1, or bigger than 1, we can have a steady state in lowercase x. Yes. let me also rewrite the vertical innovation rate and the horizontal innovation rate, equation 24 and equation 25. This is a different way to see what I was talking about when looking at the rate of returns, but there is something more that I want to say here. These are two complicated expressions, and in fact, it is good news that they are complicated expressions. Why? Because that's what endogenous growth theory is about. Endogenous growth theory is about, you change a parameter, you change the steady state growth rate. What we see here is that both Z and N will depend to virtually any parameter that is in the model. So this is what we're looking for. Importantly, do they depend on any variable? Yes. What variable? X, lowercase x. So again, if we show that there is a steady state of x, if we show that x can be constant, then we will have constant and positive Z and N. Now, x can be constant if equation 26 shows us the law of motion of lowercase x. Law of motion of lowercase x is the same as the law of motion of output growth. And it depends on z, which is a function of x, and it depends on n, which is a function of x. What does it mean? It means that we can write equation 26 as a differential equation in only one variable, that is x. And what ends up being the case is that the change in x, the differential equation, will take this form. We compress a bunch of parameters into omega 2, omega 1, and omega 0. And what do we see? We see that the dynamics of the model are described by a single differential equation that is quadratic at the numerator, and it's a hyperbole at the denominator. Finding a steady state means, well, setting the left side equal to 0. Therefore, the denominator drops out. And so it's equivalent to solving a quadratic equation. In the paper, we showed that, in fact, there is a thick set of parameters that can guarantee a unique and stable steady state with kappa smaller than 1, kappa equal to 1, we knew that before, and also kappa bigger than 1. So the first result that we wanted to show is in here. Let me give you a bit of the intuition here, what's going on in this model. So the solution to x dot, the steady state solution implies that kappa minus 1 times z must equal to gamma times n minus lambda. What does it mean? Well, let's focus on the left panel of this graph, the canonical case of kappa equal to 1. Where is the intersection between those two curves? At 0, always at 0. What does it mean? It means that in order to have endogenous growth, in that case, in order to have a steady state, in that case with constant growth, it needs to be the case that the number of products grows at the same rate as population. We knew that before, okay? Now that's where things differ if we have kappa different from 1. When kappa is bigger than 1, then the intersection will have to occur in the positive realm, meaning the number of product grows faster than population. What does it mean? To compensate for the increasing returns, it has to be the case that the market share declines faster than the increase in market size, such that the dilution in market share compensates for the increasing returns, and that is what preserves the returns to investment constant. In the opposite case of decreasing returns to vertical knowledge, kappa smaller than 1, the intuition is exactly the same. However, the intersection between the two curves will occur in the negative quadrant. And what is the negative quadrant? The negative quadrant is a situation in which population grows faster than the number of varieties. What does it mean? It means that the reduction in market share is not enough to compensate the increasing market size. And why is that important? Because that counters the decreasing returns to vertical knowledge, thus preserving constant rate of returns to vertical innovation.
I have another quick question.
Yeah.
Maybe you don't want to answer this yet. I think there are data, at least in the United States, on the number of varieties as computed by the Department of Commerce. You should be able to compare the growth rate of that to the population growth rate. That would be a real quick test right off of, not test, estimation, so to speak, of where kappa has to be in your model.
Yeah. So we estimate kappa in a different way, and I'll show you in a second. There would be another way. We used I looked into that, but I used the BDS data on number of establishment, not really the type of variable that we are interested in. But the thing is that there's that time series is not very long, and there's a lot of variation, and so you could say anything depending on
Okay.
so that's the reason why we didn't go down that route. But we will show you that we can do the estimation without relying on any measure of n. Now, so since we want to go to the data, and lowercase x is unobservable, we want to find a variable that is observable, that is a function of x, such that we can rewrite the dynamics of the model in that variable. That variable is GDP. So we define GDP in equation 28, and we compute the growth rate. Now, the growth rate we see is a function of x and a function of the growth rate of x. To go to the data, and just to go to the data, we rely on the following approximation. 1 over x is approximately equal to 0. What is this saying? This is saying that essentially lowercase x is large enough. We believe this is a reasonable assumption. After all, if you set kappa equal to 1, that's average firm size, and average firm size of innovating firm tend to be quite high. So that's we believe a reasonable approximation. And ultimately, what this approximation does is that it gets rid of the denominator on the dependence of x of the denominator in the differential equation in x. So what it does is that it produces a second order approximation of the differential equation, which we are very happy with. So this approximation, what does it do? Well, it does two things. First, it allows us to go to equation 30 from the previous differential equation that I showed you. Equation 30 is what? Differential equation in a quadratic differential equation in x. So this is very good because we can actually ultimately bring this to the data, and it's going to be a fairly simple estimation. Next, it gets rid of the dependence of G on also of growth rate of GDP per capita on the growth rate of X. And as a result, we can write G as a function of X exclusively. Because G is a linear function of X, then it will be the case that the G dot equation is a quadratic differential equation as well. So we do the transformation, and we will be able to write a quadratic equation, a quadratic differential equation in G as the only variable. And that's great because if G is the only variable, we actually have a lot of data to do our estimation. But before I move to the estimation part, let me illustrate one of our other theoretical result that is I believe interesting per se, and that also provides the intuition for what we are doing in the estimation, what we are actually estimating. We can write the speed of convergence of this economy. And the speed of convergence in the approximated model is given by what? Is given by the equation 33. Now, the last two terms in those equations are known. They are familiar. Those are given by are the terms that would be the only terms if we took a first-order approximation of the speed of convergence. That's what the growth literature has estimated ad nauseam in the 90s. So actually, we're very happy to have that to check our results in the estimation. But also, we have this additional term, omega 2 over kappa times x minus x star. What is this saying? This is saying that our speed of convergence will depend on the position of x, relative to its steady state value. And in particular, I'm not showing you omega 2, but it's in the paper, you can look it up. Omega 2, the sign of omega 2 depends exclusively on whether kappa is bigger than 1 or smaller than 1. So what is this saying? This is saying that there is an acceleration term in the speed of convergence, and the sign of this acceleration term depends on the value of kappa. And so it ends up being the case that for kappa bigger than 1, the speed of convergence decreases in the state variable x. So if we are above steady state, the speed of convergence, the further above steady state, the speed of convergence will be slow. If we are below steady state, the speed of convergence would be quite high. In the opposite case of decreasing returns, when we are above steady state, the speed of convergence would be quite high. If we are below steady state, the speed of convergence will be quite low. Let me give you a little bit of the intuition by focusing on the phase diagram. As you see, the phase diagram looks different depending on whether we have constant increasing or decreasing returns to scale. In both cases, as we proved before, there is a unique stable steady state. But the speed of convergence, of course, differs. In the canonical case of kappa equal to 1, what happens? This is a straight line. So the change in x is proportional to the level of x, constant speed of convergence. In the case of increasing returns, the speed of convergence is very high when we are below steady state. It is quite low when we are above steady state. What is the intuition in there? Well, remember that the rate of return to vertical innovation is a function of lowercase x. What is the dependence of lowercase x on z? Well, that depends on whether kappa is bigger than 1, equal to 1, or smaller than 1. When kappa is bigger than 1, lowercase x is increasing in z. When kappa is smaller than 1, it is decreasing in z. When kappa is equal to 1, it's independent of z. So what happens if there is a shock in this economy? Suppose there is a positive shock that pushes the rate of return to vertical innovation upwards. Z will increase, and there's going to be an additional effect on the rate of return to vertical innovation. In the case of increasing returns, there's an additional upward push on the rate of return to vertical innovation. And as a result, the vertical innovation channel attracts resources that are diverted away from horizontal innovation, making the convergence dynamics quite slow, because the convergence to steady state depends on the entry rate, right? Instead, in the case of decreasing returns to scale, what happens? Well, if there is an increase in z, there is a reduction in the rate of return to vertical innovation. therefore, resources are diverted away from vertical innovation towards horizontal innovation, and we go to steady state faster. If I explain the same thing with a shock that pushes us below steady state, then everything is reversed. And this is what gives us the asymmetry in the convergence dynamics.
And, Filippo, by the way, in the increasing returns case, you also may have an explosive path, right?
Yeah.
So if initial x is on the right of x bar, then there will be no convergence, which I think it's also interesting here.
It's also interesting, you know,
Yes.
the way I thought about it is there something that people have been talking about? If you think about the only thing, I don't know if it's right, but the only thing I could think about, you know, those crazy people in the Silicon Valley, they talk about singularity and this stuff like that. They may have in mind this unstable steady state.
Yes, and goes back to the economic interpretation of X John was talking about. So if you have this very large X, this links to the marginal returns and marginal profit and so on and so forth.
So that's a case in which what's the economic intuition behind the explosive steady state? That's a case in which there are increasing returns, and the vertical knowledge is so high that the vertical channel attracts so much investment that the horizontal channel cannot keep up with,
and
so we end up
destabilizing the process.
Yeah. So that's what we do. Now let me tell you that since we are on it now, we can estimate where that thing is. We find that explosive steady state is at a rate of growth that is about 8%. And we're talking about 8% rate of growth driven by innovation. So because that's what we have in mind. So that gives us some quantitative idea about where, you know, our model estimate allows us to estimate that number. One of the implications of asymmetric convergence dynamics is this. Suppose that think of a mean reverting MIT shock. In fact, think of two mean reverting MIT shocks, one after the other. One is positive, the other is negative, and you know, except for the sign, they're equal in all respects. What happens if we can compute after those two shocks have died out, we can compute what's the average growth rate in the economy. And what we find is this. Well, if kappa is equal to 1, convergence dynamics are perfectly symmetric. Therefore, the average growth rate in the economy is equal to the steady state growth rate in this economy. If there are increasing returns, what happens? If there are increasing returns, then convergence is lower from above than it is from below. And as a result, if there are these shocks in the economy, it will end up being the case that the average growth rate in this economy is above the steady state growth rate computed in the model from the average parameters. In the case of decreasing returns to scale, the opposite is true. Convergence is very slow convergence is slow from below, and it is fast from above. And as a result, the average growth rate in this economy will be below the steady state growth rate. In other words, the presence of mean reverting MIT shocks ends up being a determinant of a long-run growth. What this tells us is that one conclusion we draw from this is that, well, in the presence of non-constant returns to the growth driving factor, studying the steady state is not enough to understand long-run growth. We would also need to study changes in the parameters and convergence dynamics. Let's now go to the data. We have, as we said, a differential equation that is quadratic in X, and we showed that subject to an approximation, we can also transform it into a differential quadratic equation in G, that is GDP per capita growth. And so we write it like this, and we show in the paper that the coefficient associated to the quadratic term is uniquely pinned down by the value of kappa. So that's great because it tells us, well, let's go to the data. Let's estimate that var kappa 3 coefficient, and we uniquely pin down the value of kappa. So that's what our empirical exercise does. Additionally, if in that equation 34 we set growth rate of income of GDP per capita equal at time t and at time t minus 1, then we can compute steady state G. So we can have a measure of steady state GDP per capita growth that we find from the data directly. We do this estimation in a panel of 21 countries. We chose countries based on, are there enough observations? We look for at least 100 years of data. And also, are they likely to be around the knowledge frontier? We don't want to choose countries that are growing for a large period of time because of classical growth dynamics and so on, because that would bias our estimate. And so we end up with this panel of 21 countries that are fairly reasonable. The only one, let me point out now, that I was a bit undecided whether to add or not, was Uruguay. And in fact, we will see that Uruguay is the only one that shows weird results. But let me just tell you that if I exclude Uruguay, we get the same results. So we're not really concerned about that. We do some filtering of the data, and our preferred filtering is the HB filter. That is what will end up giving the more the results that are more in line with the literature in regard to the linear approximation of the speed of convergence. But for robustness, we also run the same thing on unfiltered data or on data filtered using the Hamilton filter. We find a very similar value of kappa, so we are pretty happy about that. Let me show you the results. The results show us that we have increasing returns to the growth driving factor, meaning kappa is bigger than 1. Specifically, it is equal to 1.47, so it's a pretty substantial degree of increasing returns. And we also find a linear approximation of the speed of convergence that is 2%. We're very happy about that because that's very much in line with the literature, so that gives some validation to the estimation. As I said, we can also compute, since we run this model with fixed effects, we can compute steady state growth rates. And because there are fixed effects, we can compute steady state growth rates that are country specific. So that's an interesting thing that we can look at to see if we can further validate our empirical strategy. Let me just add you that the standard errors on the constant terms in the regression on the fixed effects are pretty large. So the steady state growth rates will end up not being statistically different one from each other. We will just focus on looking at the point estimate because we just wanna find, are we getting results that make sense or not? That's the purpose of looking at G-star. So let's look at that. We find you can look at G-star for the US. That's 1.5% steady state growth rate over a period that goes from 1870 to 2019. That's fairly reasonable. What can we look at furthermore? Well, what are the countries above the US? What are the countries below? When we look at countries above, there are not that many. There's Canada that is not too far above. There are the Scandinavian countries, so Norway is an example there. If we look at countries that are below, what we find is typically Southern Europe. So France, you see, is at 1.16. Italy is at 1.04. Greece is at 0.20. and New Zealand, Argentina, right? So everything seems to, at least, you know, if we look at the ranking of the countries, let's disregard Uruguay for a second. I'll talk about it at the end. It looks like this can make quite some sense. What can we do next? Well, as we said, the model predicts that in the presence of shocks, there would be a difference between steady state growth and average growth. And so, specifically, when the kappa is bigger than 1, the steady state growth will be lower than the average growth. So we can look at the data on average growth and compare that to steady state growth. And we look at, again, disregard Uruguay, we see that G bar is above G star for every single country. How far above? Well, for some countries, it's not very far above. The US, it's 0.1 percentage points, so it's not crazy far above. But for some others, it is quite far above. Those that may say, you know, these are countries that have been hit by stronger or more frequent shocks. An example is Italy. We go from 1.04 to 1.71. Another example is Germany, 1.85 versus 1.20. Another example is Greece, 1.65 versus 0.20. Let me now address Uruguay. That is the result that is striking. As you see, the steady state growth there is crazy high, 2.21. It sounds a little bit unrealistic. What can be going on there? Well, suppose Uruguay is growing to a large extent because of neoclassical, in this sample period, because of capital accumulation, the neoclassical story. The neoclassical story is one of decreasing returns. So suppose that the real coefficient on Uruguay was decreasing returns. When we estimate the coefficient from Uruguay and another other 20 countries, we find increasing returns. And if we impose increasing returns on a country that actually all of the other parameters that are country specific are consistent with a decreasing return story, then we vastly exaggerate their steady state growth rate. So that's the way in which we can rationalize that Uruguay result being offline. As you see also, the G bar, the average growth rate, is lower for Uruguay compared to the steady state growth rate. And so this is further evidence of, well, there may be decreasing returns going on in Uruguay as opposed to the other countries, and possibly because this is not a country that has grown in that sample period because of knowledge accumulation, but maybe because of some other factor accumulation. All right, so this is what we have. The contributions in this paper are 3, in my opinion, in our opinion. Existence of an endogenous growth, constant growth equilibrium with increasing, decreasing, and constant returns to scale with a thick set of parameters. Nonlinearities and asymmetries in the speed of convergence that have some implications for our understanding of long-run growth of income per capita. And the estimation that comes from understanding the nonlinearities in the convergence process that can allow us to determine what the returns to vertical knowledge are. So this is what we do in this paper, and I thank you very much for your patience. And if you have any question, we are here to answer.
I have a question.
Oh, sorry, you go first.
Does your theory have anything to say about the increase in the growth rate of developed countries since the beginning of the Industrial Revolution?
What we don't show is that there are equilibria that give us stagnation, and so and so you can generate the takeoff in this type of model. In what we show in this paper, we concentrate only on the phase after the Industrial Revolution, and that's why we choose data only from 1870 onwards to estimate the parameters. So that's the answer to that story. But the paper that Pietro's been writing with Angus Chu explores instead that other aspect that you are asking about. Yeah.
Hi, Filippo. Fabio here. Thank you for acknowledging the discussions we had about this great piece of research.
Thank you for helping us.
No, I appreciate having these discussions. Actually, I wanted to ask you about this little x, because you said that intuitively this should be thought as kind of a quality adjusted size of firms, of innovating firms, and this plays quite of a crucial role when you make the approximation that 1/x is around 0, if I'm correct. So that could be, of course, a bit. I mean, we've been asked to discuss it a little bit because, of course, we could argue that you know, all of the startups might seem to be to pose a problem, like to support the opposite point, no? That actually innovating firms are kind of small. So do you have any kind of evidence that speaks to this issue, or if you plan to have any?
Well, the R&D spending scales with firm size in data. So if you look at spending in R&D, it's clustered around large firms for the most part. So they tend to be innovating firms, tend to be quite large in size. So that's the idea. Now let me add that disregarding the approximation introduces some interesting things in that equation, but they are more like at the third order level, fourth order level. That's interesting. But you know, we haven't explored that yet. It would be interesting to explore that in the future to see if there is anything of relevance going on in the higher order terms. But, you know, the literature so far was stuck at the first order approximation. We went to the second order, so we're already happy with contributing there, and we have an economic explanation for what the second order terms actually mean. So that's what we do. What we don't have yet is an explanation of what an economic intuition behind the third order terms, and so that might be something that I'm starting to think, and I'm not sure whether it's a promising avenue, but it's possible that in the future we'll explore that more.
I see. Fair enough. Thank you.
Can I add something? Filippo has been uncharacteristically modest here. The results that you were presenting are for the aggregate. Your question is deeper because it requires to understand what is a small firm that grows faster than average. So one could say the startups in our model are the horizontal innovators, but even that is not the answer you want. The paper that really answers your question is Filippo's job market paper. Because in his job market paper, he has idiosyncratic shocks at the firm level. So his model is capable of producing the so-called gazelles. So look at his paper, and I think that empirically speaking, that's the framework that can answer your question. The key is that once you go to a symmetric equilibrium, you're talking only about aggregates.
Amazing. Thank you very much.
And your question is about the firm level.
Yeah.
That you need a model with asymmetric firms, life cycle of the firm. So his job market paper is the best place to go.
Got it. Thank you very much.
It's not that I was being modest, and it wouldn't be me. It's just I had forgotten about my job market paper. Francesco.
May I go? Thank you, Filippo. That's very a fantastic presentation. You have been very smart, and also the paper really very nice, but also very interesting. I would have two comments clearly on the empirical side. First of all, it wouldn't be possible to share the slides because I have the draft of the paper, but the slides are very concise. And I mean, at least for me that are not properly in the theoretical side, it would be very helpful to get into the details. So I have two comments. One, I think that this contribution is very helpful also for the, I mean, there is a literature coming from Johnson, Papageorgiou on income convergence in journal economic literature that shows that this somehow reopened the debate on income convergence, growth convergence. And there are two very influential papers, Kramer and Patel in Journal of Development Economics 2021, that show that convergence is not non-linear. So there is, I mean, you see convergence, but following an inverted U shape. I mean, your paper makes a contribution also on this side. So you empirically use data for the country that somehow have completed convergence along their path. But maybe I think with the model you can make a contribution also on the literature on development economics, where there's thing that convergence is not linear, and basically there are some polarization, and where in the middle of the distribution, countries are no longer able to converge. So you find convergence on one side and convergence towards the bottom on the other side. And this seems that it also like a power law, because some similar evidence come out also on original data. There are some a paper by Sibona Iavarino, Rodriguez Pose, that shows somehow a similar kind of a convergence pattern within Europe. So an inverted U shape. So a given point, middle income countries get stuck and they are not able to converge. So I'll go to the, I mean, my first comment is that you may, I mean, you strongly relate to this literature. Even, I mean, you may try to relate to this, your model, your paper to this literature, which is more on income convergence. So and expand as much as you can the audience that can learn from your setup. Secondly, my second point is about your empirical specification. You basically, because I mean, you use a dependent variable, the change in the growth rate, right? I mean, and in order to relate to the literature that was talking about, you, I don't know, you may also see to adopt a more standard income convergence equation where you have the, I mean, the GDP growth rate on the left-hand side and the lagged income on the right-hand side, and maybe adding the nonlinearity. So at that point, you would have all the ingredients to relate also to the other literature that I was mentioning. So I mean, this is what I see in, I mean, that very useful to link. I mean, I think it could be nice to that you can link your paper also that quite influential empirical literature that, I mean, is quite because there is a lot of interest on nonlinear growth pattern empirically now. So I think your model or your empirical analysis can make a very significant contribution. So I'm really very sorry that I will hear Filippo reply, then I will have to go. And I want to mention just one word, an initiative that we are organizing in Urbino, where I work with Pietro, Maurizio, Antonio, that Antonio will speak later about it. Sorry again for my long
Okay, yeah, thank you very much, Francesco. I think I will ask you later. I will send you the slides, and I will ask you later some of the references. I agree. We should engage with that literature, and we should look into that. But we ought to be careful because if they're talking about convergence in the neoclassical frameworks, and we're talking about countries that are quite poor, they may grow from capital accumulation and so on. That's not the type of countries that we have in mind here, because this is a paper where the action is on expanding the knowledge frontier. And so the convergence dynamics, if you write down a neoclassical growth model, and the convergence dynamics, if you write down a model like ours can be different. In fact, we did write down the Solo model, and we did write down the equation that the Solo model would imply, the quadratic equation that the Solo model would imply, and that imposes a restriction on the parameter on the quadratic term, that is, it would have to be negative. So that's something that's testable. Our theory doesn't impose any of that, right? So whatever that term is, that tells us what the value of kappa is. But we don't have we don't reject the theory when the value of kappa is below 0 or above 0. With the Solo model, yes.
Can I add something?
Yeah.
We have to be careful here, because the global dynamics of this economy, so the differential equation is piecewise. There are 3 regions. In region 1 and 2, vertical innovation is not active. So my personal interpretation of this model before the activation of vertical innovation is that it is like a neoclassical model where the role of capital is played by the number of products. So if I interpret the firm as a unit of capital, so the model, in fact, does predict a U-shaped convergence pattern, because before the onset of vertical innovation, the quadratic differential equation would exactly have a negative coefficient on the quadratic term. So there is an inversion of the sign when there is increasing returns to the aggregate. We didn't go there, but I'm not sure that I understood exactly the U-shaped pattern of convergence that Francesco was mentioning. So we need to read the paper before we can say how this work relates to that. But the model definitely predicts an inversion in the even in the predicted sign of the regression.
Yeah, that's essentially what John was asking earlier.
Yeah, that's the connection too.
Yeah. So yes, so that's I think that's a good point. Maybe there is something to investigate in the region of vertical innovation.
And one thing, when Francesco was describing the inverted U in that paper that he mentioned, it looks like that inverted U that they were talking about gives rise to convergence clubs.
Yes, that's the interpretation I was giving,
this
right?
This model can generate convergence clubs if you allow countries to have different parameters. For example, you can imagine a subset of countries that never makes it to the 3rd region with vertical innovation because of institutional things. Maurizio and I have written about that in our paper on corporate governance industrialization. So these are possibilities. There are going to be different narratives from whatever comes from neoclassical models, but we need to read those papers. At least I do.
Okay, can I ask you a question?
Mm-hmm.
Yes, I would like to ask you the technical question. I'm very impressed to know you derived quadratic differential equation by assuming kappa is different from 1. In case of kappa is 1, yes, you will get the linear differential equation as usual. But if you depart from kappa from 1, yes, you derive the more rich interpretation. But in case of a quadratic equation, it's possible that no real solution exists. It depends on the parameter. Yes, in case of quadratic equation, the solution of x dot equals 0. In some cases, you will get 2 real solutions. In case of just one real solution or no real solution, imaginary solution, you assume you always get the 2 real solution. What will happen if depends on the parameter, and if you do not get any real solution? Yes. So this graph is above the zero. Above zero. In this case, there is no x star or x tilde.
Yeah, so what we show in the paper is that there is a thick set of parameters that gives us the solution, but there could be parameters combinations that give no real solution.
Yes, of course. Yes. If what parameter is most important to get the real solution? Do you find?
Well, I can answer the question by showing you this.
Yeah.
All of them. So it's a combination of parameters. I don't think I can answer your question by telling you a specific parameters, but let me tell you that we calibrated the model. We don't show it in the paper, but we did the calibration. And we encountered that problem sometimes with some combinations of parameters or with some targets. The parameter that was quite important to have in the model in order to have a higher chance of getting a solution is this zeta parameter here.
Yeah, I think this is, in my opinion, I think this is potentially very interesting because, yes, if you have the real solution, yes, you will have the convergence state. But if something happens and due to some parameter change, if you do not find any real solution, the dynamics is changed dramatically. Personally, I'm interested in this. But generally speaking, yes, your finding by considering kappa is different from one. Yes, you get the quadratic differential solution, and I think this is very interesting point.
Yeah, that's what we found interesting as well, and that's what allowed us to go to the data, precisely having that. But yeah, you're right. I think so. The answer is, well, if where is it? That parabola is always above zero, then there's an ever increasing x, and so you have explosive growth. So that's you don't have a steady state, right? So this is the type of thing, and so. With those parameterizations, we go back to the case of to the understanding of increasing returns giving us an explosive model.
I see.
Well, we show that in the paper there is that region specified that the set of parameters that gives us a real solution is quite thick.
I got it. Thank you so much.
Yeah. Any further questions?
Okay, Filippo, there is some, there are some comments in the chat. So
I didn't see them.
Yeah, you can read later on. So maybe...
there are 14 comments in the chat. Okay. Maurizio asks, in case of kappa bigger than 1, the distance between x star and x tilde goes up or down with k, with kappa. Okay, so Pietro replied. Antonio, in slide 20, since the speed of convergence is not constant, perhaps using arrows in the phase diagram could keep, we are in slide 20 exactly, could help us illustrate the different speeds in the 3 cases. Yeah, I think it is. That's something that that we can think about adding in that graph. Chris says he's leaving. Okay. Okay, Francesco sends us the thing. Maurizio. Okay, Pietro replied to Maurizio. Okay, so we have covered everything, it seems to me.
Yeah, just thanks a lot, Filippo, for the presentation. So
thank you.
Post this video on YouTube. So just some words on the summer school that we are organizing with Pietro, Francesco, Carmelo, and Maurizio. So we are organizing a summer school that will take place in Urbino, at the University of Urbino, in July 2025, so this year. So the summer school is for PhD students and also early career researcher. So we try to offer a balanced mix of theoretical lectures and also practical sessions on data analysis and also simulation in the afternoons. So key topics include market structure, growth, interaction between taxation, public debt, and markets. So Pietro Peretto will be one keynote speaker, and the other two are Marcus Eberhard from the University of Nottingham and Andrea Presbitero from the International Monetary Fund. So if you have students or if you want to attend, you are welcome. And also I posted the link in the chat, so you can find all the information in the main website. So thanks a lot to everybody.
Antonio, if you can stop the recording so that we can have a more private conversation.
Yeah, I can do it.
Yes.
We are about to say nasty things about some people.
Well,